Okay, thank you. I'm Marco Castellano of the Astronomical Observatory of Rome. First of all, I would like to thank the organizers for giving me this opportunity to be here at this very... Oh, sorry. Yes, he made me start. Oh, just... Okay, thank you. Well, I wait for the people to be back. I'll try. Okay.
So we're going to hear we're going to hear about this nooning of gas information from predicted by MOND.
Thank you. So thanks for giving me this opportunity to be here at this very stimulating conference. I'm Marco Castellano, Astronomical Observatory of Rome. I will discuss about the first generation of galaxies as seen from GWST observation. So first of all, while looking at the very high-redshift universe, very schematic slide in this respect, we know more about how the star formation rate density evolves throughout cosmic time up to a redshift of 8 or 9, but there are things supposed to happen beyond that we don't know much about. We know nothing actually. So at some point there will be the first generation of stars forming, and in the very early universe even the formation of galaxies and structures can be strongly affected by the cosmology, and I just wanted to put let's say a wild example from this model with primordial black holes and ΛCDM, but just to highlight that in these very early phases, the very first 100 of million years, the formation of structures can tell us a lot about cosmology too. So why GWST? Basically GWST has completely opened a new window that was previously not accessible to our observations. So the ground-based telescope and then the Hubble Space Telescope could reach up to the reionization epoch, up to about a redshift of 10, but what happened beyond 10 was not accessible, while GWST, thanks to its sensitivity, gives us this opportunity. He has a sensitivity that is even a factor of 1,000 higher than previous instruments, depending on the observing mode and the exact wavelength, but it's really transforming to observe the near-infrared and the mid-infrared compared to Space Telescope and the Spitzer Space Telescope. This was the situation with Hubble. This histogram gives you the number of sources selected with Hubble Space Telescope. The Space Telescope can select galaxies thanks to the Lyman break, which is indicative of star-forming galaxies up to about a redshift of 10. This was the most distant galaxy confirmed with HST GRISM spectroscopy. And JWST, in just a few months, gave us a lot of candidates at higher redshift, thanks to the capability of selecting the Lyman break and also the Balmer break up to a redshift of 10, and the Lyman break in principle even up to a redshift of 30. So it's really a completely new capability. And just an example of a star-forming galaxy selected with HST that was supposed to be, this is the photometric redshift distribution, estimated to be between 7 and 9, and this was in the HST images and Spitzer, and this is how it looks like in JWST. So to highlight how JWST is really transformative to observe this very early population. So the results I'm going to present, first of all, come from the GLASS-JWST early release science survey. It was one of the first surveys to be observed, so I had the opportunity to be one of the first looking at the JWST data. This is a picture of me with the PI of GLASS, Tommaso Treo, and our group leader, Adriano Fontana. And then other observation came in the same area, NIRCam observation, so near-infrared observation in this area of the strong lensing galaxy cluster Abell 2744. The first epoch observation was this small field up here highlighted in green, one of the two fields highlighted in green. What did we do? We selected Lyman break galaxies with the standard Lyman break technique. Basically, you look for the Lyman break, so a high color term where the Lyman break is expected, and a flat color here indicative of the typical UV shape, non-ionizing UV shape of star-forming galaxies. Some candidates were found, but the two highlighted in these slides were really surprising. These are the two galaxies. This is from NASA press release image. The two objects are a candidate at redshift 10.5 and another estimated to be a redshift 12.5 from photometric redshift. What's surprising about these galaxies? So at glance they have different properties. They are, this one, the redshift 10 one, is quite extended, like disky shape, flat UV slope. The other is bluer. It's incredibly compact. It's 100 parsec effective radius, but the most surprising thing is their brightness. They are very bright. It's about -21 in NUV, and this was completely unexpected. So to be honest, we did not expect to find these galaxies. Personally, I was even worried that we were not going to find anything in this very first of observations, because this field is only 6.5 square arc minutes of area. So any estimate was giving a very low chance of finding galaxies of this brightness in this field. This was surprising. We compared in our first paper, this was the very first galaxies selected in JWST observation. So we had this opportunity few days after we received the observation to present this paper. We compared the expected number density to available predictions. So the number of galaxies we found is two objects, but predictions from extrapolations and also we show from models. This is an example, quite an old one from 2011, but you can see that we expected no objects that bright or even bright as the ones we found. So this is not only characteristics of this field, it's not luck, because it has been found in several other observations. This is a work by the Japanese group, by Yuichi Arikane. They analyzed the glass field and other early release science observations, collecting luminosity function from redshift 16 to 10. They find a very mild evolution of the bright end of the luminosity function. This was a prediction from a model dating back to 2015, and as you can see, the luminosity function at this redshift was predicted to evolve very rapidly, very different from the observations here. This was a collection of fields including GLASS. This is a field independent of GLASS. This is the Sears survey, a paper by Steve Finkelstein and the Sears team. Surface density of objects as a function of redshift. with a magnitude cap. And this is compared to theoretical models. As you can see, most of the models, there is one exception, but the most famous models, I would say, they all predicted a much lower number of objects at this redshift. So very different from observation. Yet another independent field, this is the MIRI Deep Survey, Perez, Gonzalez, and collaborator. This plot is in a different units. This is the UV luminosity density, but the message is the same. This is highlighted the estimate from the objects they found and compared to the models. So there is a high abundance of galaxies at very high redshift, which was not predicted. This was, of course, noticed, and there has been basically a rush to provide explanation for these unexpected results. I will not go through all these proposed explanations ranging from a very high star formation efficiency or the presence of populations like POP3 or AGN boosting UV emission and so on. So they could manage to some extent to reconcile the models with the observations, with proposing several mechanisms for this excess of galaxies. We then proceeded to analyze the full area. The first two objects were in this small patch. We then analyzed the full Able 2744 region, and we found an even higher abundance of galaxies. These are 7 candidates at redshift 10. They are all quite bright and quite robust candidates, and this is the luminosity function we presented. As you can see, it's even higher than other estimates, including the Aricane one that I presented before. We need spectroscopic follow-up for these sources because these are photometric candidates. Luckily, our program has been approved for cycle 2, so I hope we will be able to confirm these objects. In particular, this region may even host an overdensity on top of the excess of galaxies that we have found. Possibly there is even a forming structure, but this has to be confirmed. Luckily, one of the objects in the extended area was included in the GLASS spectroscopic program itself. This is the candidate DHZ1. It's confirmed, redshift 9.3. It's very bright, -22, and massive. 10 to the 9 solar masses at redshift 9.3. Another object, very interesting, that gives me the opportunity also to discuss another part of this accelerated evolution of galaxies at early times, is this one, UHZ1, a candidate, redshift 10.3 from our paper, recently found to have point-like X-ray emission. So this other group speculates that it is hosting a supermassive black hole of 40 million solar masses and 10 to the 45 erg per second volumetric luminosity. And you can produce this black hole possibly with Eddington accretion on massive black hole seeds formed at the incredible redshift like 2025, or maybe with super Eddington accretion on lighter seeds. But this gives you again, and it's not the only result in this respect, another line of evidence towards this accelerated evolution of early galaxies. Another AGN at redshift 9, another at redshift 10.6 in other fields, and the plots are very similar to the previous one. Everything in these cases can be more likely explained with accretion on objects that were forming already with 10 to the 4 or 10 to the 6 solar masses in black hole beyond the redshift 15 or 20. There is another side of the coin in all of these, which is massive galaxies. So far I have discussed UV bright galaxies. So the message is there are more UV bright galaxies than expected and a lot of supermassive black holes that formed early, but a paper by Labbe collaborators analyzing the Sears survey found at slightly lower redshift a sample of galaxies with masses up to 10 to the 10, and the redshift from 7 to 10, and estimating a mass density for these objects higher than previous estimates. So this appears really as the other side of the coin compared to the excess of UV bright galaxies. So in a paper done by our group, we compared the expectation from LCDM for the formation of these galaxies. Basically, the implied stellar mass density is inconsistent with what you can get for ΛCDM, but even in considering the full range of dynamical dark energy models, this is inconsistent with a large part of the parameter space for WA and W0. Consider that these are the confidence regions for the other cosmological probes, while these in brown, from orange to brown, are exclusion regions from the stellar mass density measured by with the objects by Labbe and collaborators. So basically, this part of the dynamical dark energy parameter space would be excluded by those objects, including this point, which is of course the nominal lambda CDM, excluded at 2 sigma. There are some caveats in all of these. It's true, as we have shown, that in this paper by Santini, that JWST probing the optical rest frame gives a very good estimate of stellar masses at very high redshift, decreasing the uncertainties by even a factor of 10 or more. But this is concerning statistics, but systematic uncertainties may arise due, for example, the presence of strong emission lines in the optical rest frame boosting the flux. So if this is the case, masses can be overestimated, and this has been speculated by Hensley and collaborators. On the other hand, there can be an opposite effect, because this other paper, Jimenez-Arteaga, very recent paper, has shown that once you do resolved analysis of the spectral energy distribution of the objects, you indeed obtain even higher stellar masses. That's because the integrated light tends to underestimate the age of the object. So instead, a resolved analysis gives a more accurate masses. So integrated light masses are underestimated. So this goes in the opposite direction. So it's possible that, although these objects are not yet confirmed by spectroscopy, it's possible that this tension with cosmology is very real. And of course, to conclude, there are several lines of evidence for this accelerated evolution of galaxies in the early epochs. This is not only the excess of UV bright galaxies that we have been found in the GLASS early science survey, but also in other fields. There is this excess of masses. So the question is this evidence for accelerated galaxy formation as proposed in MOND by Sanders 98. Ideally, we will need some detailed comparison with predictions concerning properties and luminosity function of galaxies in MOND scenarios, but keep an eye on these evolving results from GWST. There are some other lines of evidence I didn't have the time to present for this accelerated evolution, and I think then for coming period will give us even more results in this respect. Thank you.
Thank you. Any questions from the audience? Keith got it first.
You concentrated on estimates for number density and brightness, but I think there's also a surprise in the estimated sizes of these objects. Aren't they incredibly small compared to what you expect a galaxy to look like at that mass?
Yeah, it's true. Indeed, one of the objects, the redshift 12 objects, is incredibly small, maybe an AGN. That's 100 parsec effective radius or less. Yes, you're right. But I honestly, I don't know what the implication can be from this. There is another aspect. I think this is shown here, that I was prepared for the other lines of evidence, which is also not only the sizes but also the morphology, because one other result from GWST was an early formation of these galaxies. So this may be referred to as slightly lower redshift. But it's true that morphology is also something to be addressed. But honestly, I don't know how to interpret this.
We have a question from Federico.
Very beautiful results,
And then
Marco.
next question.
So I have a question about the UV bright galaxies. So I have a question about the UV bright galaxies. You mentioned the possibility of population 3 stars, which is, I think, very serious, because population 3 stars must have existed at some point, and we know almost nothing about them. So what is your take on this? What constraints could we put on POP3 stars?
So at present, lacking spectroscopic follow-up, I think we cannot say much about POP3 star. There has been a claim like a few days ago by the JADES group that they have found evidence for a very high equivalent with helium-2 emission close to, actually to this guy. Where is it? This one is an AGN, but it's, well, this is hosts an AGN, it's also a star-forming galaxy. And Maiolino and collaborators, the same team that did this paper, close like like 3 kiloparsec from the center of the object, has found an helium-2 line at the same redshift with a very high equivalent width. And the claim is that's evidence of a clump of POP3 stars close to GNC 11. This is like a few days ago. So we need spectroscopy for that. It's possible that in the outskirts of these bright galaxies there are POP3 stars. It's possible that the faintest ones are even dominated, but we need spectroscopy.
Last question from Ricardo.
Very nice work, and of course I take on the comment made before. These galaxies are computed to be extremely small, but this result completely depends on the cosmology that they are using. Of course, your data are showing that ΛCDM is not working. This is what your data are telling you. And okay, no one is willing to get rid of ΛCDM. We can modify Einstein, but we cannot touch the Big Bang. I don't know why. Wait, do you have the answer? I gave you the answer yesterday. Change cosmology, and you will see that all these weird things the galaxy do will disappear. And these galaxies are actually very normal, equivalent to the Milky Way redshift 12.
I get your, okay, I get your point. Okay. Oh, just a very quick comment. Oh, okay, I get your point about sizes. Concerning the evolution, though, I think we would need two other mechanisms changing cosmology. So either there is more time for these galaxies to form, or there is some way for these galaxies to form faster. Concerning, well, unless the universe is static, okay.
The time is defined by the cosmology. At redshift 12, in the static case, the age of the universe is, the look-back time is about 100 billion years. So you have plenty of time to form all the stars that you want and all the galaxies that you want.
Okay, that may be
So
the
let's
answer.
make it clear. It doesn't have an answer for that. Yeah. Okay, so thank you.
Thank you.